Okay, so welcome for the afternoon session with Lorenzo Rosasco from MIT and Genova University. And we're going to speak about regularization methods for large-scale machine learning.
It's true. Right, so thanks for having me here. Thank Gabriel, Johan, Guillaume. Can you hear me okay? So yeah, so I'm gonna bore you for 4 segments, and these 4 segments we're gonna go from somewhat more established stuff. It's gonna be more pedagogical material that is a bit older, basically today, and it's also gonna be a bit slightly more technical. And then tomorrow is gonna be somewhat geared to towards recent stuff and more algorithmic issues. Broadly speaking, my background is machine learning. So that's what I've been doing for a while. And then in the last few years, I've been doing a lot of optimization, as you see in the morning with optimization. We start to have very big data sets, and we start to have the problem that you optimize. The statistical aspect is important, but now how to handle big data sets become as important. And then one of my old passion and how I started dealing with machine learning was inverse problems. And it turns out that as I start to do learning and optimization more and more, I got back to inverse problems as a way to think about what I was doing, basically. Inverse problem is a very general framework to deal with a lot of different applied math problems, and you've seen in the morning several examples. And here the typical issues are related to stability with respect to the data that are somewhat corrupted with some form of perturbation. Whereas in optimization, most of the anxiety is just to be fast and go somewhere fast and optimize fast. And then I found myself somewhat thinking, well, do I really want to go that fast there when I have to deal with noisy data? And this was not only just because I would think about myself, because there has been somewhat this trend in machine learning about thinking at the same time a statistical issue together with computational issues, and basically asking the question whether do you really want to solve things with infinite numerical precision, or you should somewhat think a bit more in terms of how much precision you actually need when you're dealing with empirical problems that are already corrupted with some form of, say, noise, sampling, or other kind of corruptions. So this, as simple as it is, just raising this question, how much precise you want to be in your numerical computation, somewhat shift gears and force you to think at the modeling aspects and the computational aspects, not as separate steps, but as somewhat as at least interfacing step, hopefully at the same step, okay, just one single procedure. In my view, inverse problem has been a way to think about this in a kind of coherent way, and so that's what I would like to share with you. Okay, so this is just some blah blah. Hopefully by the end of today will make more sense, and by tomorrow you should see the whole story appearing. So the set of lectures is going to be, as I said, 4. The first part would basically be learning an inverse problem. Okay, I'm going to try to find a way to translate learning as an inverse problem. I'm going to have to go, it's going to be a bit painful because we have to define learning, define what is a linear inverse problem, and then try to find the connection between the two. And we're going to be a bit abstract for today. The second step is going to be, okay, fine, I've done this. Okay, we'll achieve some kind of connection, and then we'll try to say, what can we do with it? Okay, and the typical attitude is going to be, can we steal from the world of inverse problem? What can we steal? How much work we have to do more once we move from inverse problem to machine learning, and how much we can just steal. And the thing we start to steal are going to be algorithms, in particular regularization techniques. And when we're going to discuss regularization techniques, we're going to emphasize immediately somewhat the statistical aspects in terms of statistical guarantees, and then the computational aspects. The first round is going to be essentially Tikhonov regularization, the most classical one. It's going to serve as an excuse to introduce a bunch of ideas and concepts. The game we're going to do from today on is basically going to say, okay, are there other principles to design algorithm? This is the first principle to design algorithm. Are there other principles? And it turns out that indeed the answer will be yes. And then the natural question is, how do you compare the different algorithms? And the story that will arise will be essentially the following. All the algorithms we're going to present from this moment on are going to be essentially equivalent from a statistical point of view. They're all going to be very good. They're going to be optimal, in fact. So we won't be trying to improve them from a statistical point of view. We're just going to try to shave away computations, to go from high computational cost to lower computational cost to achieve the same statistical accuracy. We would love to know what is the optimal computational cost. We don't know, so we're just going to go on and shave more and more cost, and along the way, hopefully learn something. So tomorrow, the first part is going to be essentially related to what is called iterative regularization. Now I start to write badly. Now let's keep on writing nicely. Iterative regularization is what is sometimes called also early stopping, and the way I'm going to try to present it is to convince you that it's not just a trick or a hack, but it's actually a nice meeting point of optimization and statistics. It's a point where they just meet, and a lot of different questions somewhat arise from thinking at the same time in terms of convergence from an optimization point of view and robustness from an optimization view that you like. The last step is going to be mixing all this with stochastic projections. Up to now, up to this point, we're primarily going to think about improving time complexity of our algorithm, keeping the statistical accuracy the same. From this moment on, we're going to try to also reduce the memory requirement. We're going to try to see if there are favorable cases when we can solve a problem with the optimal statistical accuracy, but at the same time substantially reducing the computational costs. Okay? And the nice thing of this is that in all these steps, we're going to really see how essentially extract pieces of knowledge from the theory of inverse problem and mixing it up from modern statistics and machine learning. So this is the menu for the whole 2 days. The menu for today is going to be essentially, as I said, that I'm going to start to introduce learning, and I'm going to do it in the framework of statistical learning theory, and in fact in a subset of this framework. And essentially, if you want to call it regression with random design, that's fine too, and that's just nonparametric, the typical setting of a nonparametric regression. I'm going to introduce the inverse problem. And then I'm going to describe, as I said, the connection between the two. This connection is going to be somewhat abstract. It's going to be formal in a way. We're just going to recognize objects. And so the last step is going to be some, let's call it extras, where we try to understand a bit more the nature of this inverse problem that arises in machine learning, what it is, have we met it before, what are the nature of the objects involved in the definition. Okay? I sent Gabriele I sent around a bunch of notes I wrote. It's a superset. It's by no means finished or polished, but it should be enough for most of you to have something that you can use without having to spend too much time writing and spend a bit more time thinking. If you have any question at any point, or if you see mistakes, which is quite likely, especially because it's hot and I'm writing on the board, just stop me. Okie doke. So, as I said, our job is going to be a bit tedious for at least 40 minutes or so. We're going to introduce a theory, then we're going to introduce, or let's say, a framework, then another framework, and then we're going to connect the two frameworks. So how many of you are familiar with statistical learning theory? All right. So what we mean by learning, there are a bunch of things. It's essentially some kind of mix of statistics and computations. Okay, the community is equally divided in people that ignore statistics and just love to do algorithm, and the other way around, and some people that try to work in the intersection. The kind of problem I'm going to look at is a very basic and it's very general, and it's the idea to try to learn a function. So this is just some warm-up. Okay, I'm going to have to learn a function from some input space to the output space, and I'm given some pairs of input and output. And for now, I'm just sloppy about the nature of this point. There are input and output. The y's are some possibly noisy version of f of x. Okay. we just want to appreciate at this level that this is actually a fairly general class of problems. It's not just a simple problem, because depending what you put here and here, you're basically looking at the problem of estimating vectors, matrices, tensors, function, scalar valued, function defined on, for example, Hilbert spaces, so functionals, or more general operators, okay? It's fairly general. Most of what we're going to do today is going to restrict this to be the real numbers. But most of the techniques that I'm going to present somewhat extend, say roughly 70% of the ideas extend to settings that are way more general, okay? So it's a simple problem, but it's actually a lot of problem at once. And we're going to try to emphasize what's common among all these problems. The list of problems that you can face this way is literally endless. If you want to recognize different text, you have, say, emails that are spam and not spam. You're given the text. You've been clicking spam for a while whenever you see one. You've been saving right emails for a while. Then you want a system that is adaptive and is basically going to be able to say automatically whether an email is a spam or not. How do you do it? You take a bunch of emails which are spam, a bunch of emails which are not spam. You turn the emails into vectors, typically doing some kind of word counting. And this is going to become your X, okay? And then you just put a label, 1 or -1, whether it's a spam or not. Now, take the same idea, take my face and his face, images, okay? You're going to save a bunch of my faces, images, say, 20 by 20, his face is image 20 by 20. You get 400-dimensional vectors if you unroll the pixels into big vectors. They're going to be your X's. And then you have my face, his face, -1. And then this is cases where the output is, say, binary, but you can assume that you can take a continuous score, or you can just assume some kind of different kind of problems where the output is real. Everything I'm going to discuss is mostly geared to the case where you just have real valued outputs. Again, if they're binary, we can discuss this, and I somewhat put some, it's easy to adapt whatever I said to that case, and in the notes I give some pointer to how to do it. Okay, so this is just to give you a vague idea. That's your question, yes? Absolutely, yes. So the problem is that there is some unknown function, and all you're given is this, and you would like to estimate that. And we have to make this problem slightly precise, we have to make some more formal assumption relating this data to this. And that's what I want to do next. What I'm going to try is actually a relatively short definition, but it's somewhat dense conceptually. So this is just to give you a rough idea. There is a function. It's fixed, but you don't know it. And all you're given are some inputs and some outputs. Find the function. OK? Other questions? So let's try to make this precise. I can write the problem in a pretty compact form. Before doing it, let me emphasize one key point. I'm given data today, but my goal is by no means just predict the data I have today. If you want to do an app that put a little square around the face, you just don't want to do it on the data set that you collected up to tonight. You want to do it so that tomorrow you just do like this and you recognize a face. Okay? If you want to do your spam, you just don't want to recognize the spam you already have. You want to recognize new spam. As simple as it is, this is the key of learning. From some experience, you learn how to solve the same problem in the future. So this is going to cost us some gymnastics because you have to talk about what does it mean the future, the past, where is the data coming from. And we're going to do this in some kind of a probabilistic framework, assuming that the data come from some underlying distribution. We're going to have an ideal problem that we would like to solve, which is something that works well in the future. And then what we can do, which is just what we have today, which is going to be the data. Okay? So we're going to write mathematically the problem, which is going to be an ideal problem that we will only be able to approximate somehow. So the problem is to solve a minimization problem among, say, all functions from x to r, where the function I'm looking for is basically an expectation. So let me finish writing, and then we comment on the various pieces. Okay, so first thing first. The nice thing about this is that there are just 3 lines, but the 3 lines are dense, so we have to go them step by step. We're going to assume that the output is just the reals, and we can be pretty general about the input. Okay? You need a bit more than a set. You need some topology and essentially be able to define probabilities. But if you want, just think of X as RD with a D large. Okay? Then what do? We say that our goal is to minimize some functional. Let's look at the functional first. The functional is the average mean squared error, where the average is taken with respect to the true underlying distribution rho. If you find an F for which this quantity is small, if you could do it, then it means that you're going to have a small error in the least square sense. And particularly, you're going to have that points that are more likely to be sampled are going to count more. So if point never appears, you don't care about that point too much. But if point appears a lot, then you want to weight that more. This is all what this is saying. And the fact that we allow ourselves to, in principle, look at everything, again, we're being theoretician now. Basically, this is the way we say this has to be good in the past and in the future. It has to be good for everything. And this is ideally, arguably, what you would want to do. Okay? The problem is exactly to find them all possible function. Here I just say all possible function. It's a minimal, say, measurability or integrability condition to ensure that this object is well defined. We don't want to dwell with that detail. So the basic idea is that among all possible functions for which this is well defined, try to find the one that minimizes this error. Okay? Ideally, this is what you want to do. Because again, if you could do this, then you have something that will work well all the time. The key point is that the distribution rho is, as we said before, fixed, but is not known. I don't have it in a closed form, or I don't have access to it. All I have is a set of samples, okay? Xi, Yi. And I assume this sample to be sampled according to the distribution rho in an independent way. So rho, if you want, is a rho of X and Y, and I'm going to take pairs X and Y according to this distribution, okay? And each one is going to come exactly from the same distribution and is going to be independent to the other. These two assumptions are not equally, they're both strong, and they're not equally, so we could weaken one, but another one is very important. So the idea of independence, we could somehow weaken it, assuming some kind of form weak dependence among the sample, and basically everything I'm going to say is going to change not too much. But the idea that all the points come from the same distribution is arguably more important. If we make this point come from a set of changing distribution, we're just in a different ballpark. Okay? So for today, we're just going to stick to the standard statistical learning theory setting where the distribution is fixed and unknown, and if you want, the data are IID, identically independently distributed. Okay? All right, so this is the basic problem. I'm given an input and an output and a distribution over the input and output space. Among all possible functions, find one that should minimize this, but in the case where you don't have access to distribution, but only to n samples from distribution. Well, clearly, I have no hope to solve this problem exactly. I only have a partial information, and I will have to define in which sense I can solve it. What is a good metric? And since everything is stochastic, in which sense I want to solve it for? If I call this a training set, do I want to do this for every training set, for the worst training set, for the training set on average? We have to agree on that. We're going to do this in due time. I stick to the square loss, and everything I present today and tomorrow is going to be for the square loss. I'm going to point out here and there how and when you can generalize. Basically, the clean connection between inverse problem and learning is going to be really exploiting the square loss. We can take one step further before moving on, because in this element of generality, in fact, you can basically try to estimate analytically, again, hallucinating for 1 minute and assuming that you know the probability distribution. If this distribution now it's decomposed, which can be done under very, very general assumption in a marginal on the input and the condition on the output, then we know that the best possible solution to this problem is actually what is called the regression function, which is defined almost surely as the expected conditional mean. Okay? Now think a second about it. You're basically saying for each point, I'm going to look at the distribution of all possible outputs and take the mean. And you take the mean because we took the square loss. Whenever you take the square loss, you know, when you derive, the square goes away, you get something linear, you get the mean. If you were taking, say, the absolute value, you would get something more like a median, and so on and so forth. So the fact that we get this is really essentially because we're sticking to the square loss. So far, so good? So this is the half-bird version of statistical learning theory. If you want, one big question at this point is, okay, how do we find an algorithm to solve this problem? Okay, we define the problem. We know that as theoretician, our job will be to prove that whatever function f you find based on the data, it should be a good approximation in this in some precise sense. How do you find it? And how long is it going to take you to find it? What are the kind of resources, computational resources needed to find this? This is what we want to ask next. And we're going to take kind of a long route to get there. So what I want to do next is basically introduce the inverse problem before trying to find the connection that is going to suggest how to build algorithms. Before I do that, is there any questions so far? This is just one of 3 steps of definition, so it's a good point to slow down and clear your mind if you have any doubt. Gabriel, you have doubts? You're good? He's been studying a lot. Guillaume complains. You're good? Everybody else, they know this stuff. Then let's play with this. This one. Maybe it's too high, but I can jump really high. All right, so what is an inverse problem? I think Emilie actually gave you a definition this morning. I'm just going to be going quickly about it. So the idea is that we're going to stick to linear inverse problem, which is going to make our life easy. And again, our second step is going to define what is an inverse problem. So I'm going to start writing in a bad way and smaller. And you should stop me at some point, okay? I become tired and become ugly, and especially you up there, you're going to either fall asleep or not follow. Stop me. Okay, so let A be an operator from a space H and a space G, and let's assume that H, G are Hilbert spaces. And I'm going to assume that they're nice Hilbert spaces. I'm going to make my life easier. They're going to be defined on the reals. They're going to be typically Hilbert spaces of function, although most of the things I say won't matter. And they're going to be separable, so that I can talk about the bases and do all my spectral theory, talk about eigenfunction and so on and so forth. Okay? So I'm not going to spell out these assumptions. These are like some of the default situation to be able to do all this stuff that we typically do. Now, what's the problem? The idea is that we want to solve a linear equation, okay? And then we have to agree what is given and what is not given. The most standard scenario of inverse problem, typically the idea is that A is given, okay? And G is not quite given. Typically, some G delta is given, which is somewhat contained in a ball or radius delta around this point. So let's draw it. So you have a space H. You have a space G. You have typically the range of the operator A. And then you have G somewhere, okay? And then in a little ball or radius delta, you have G delta. Okay? So again, mathematically it's pretty nice because it's just two lines. And it's kind of the same flavor of the one we showed before. There is an ideal problem defined some by ideal quantities, and then there is a practical situation where I'm not giving a full information. In the case above, the true ideal object was the distribution. In this case, the ideal objects are an operator A and a function G. And you see why this is called an inverse problem, because basically I need to invert this linear relation to solve the problem. But exactly as it happens there, and I'm just doing an analogy for now, I'm not given access to the exact formulation of the problem, but only to somewhat perturbed formulation of the problem, where I'm only have access to a datum which is delta away to the exact one. So my goal is to solve this, but I can only settle for an approximate solution because I don't have access to this problem. A few comments. First of all, this setting encompasses a list of problems which is, again, endless. Okay? So, say, a lot of imaging problems like denoising, the blurring, in painting can be formulated this way. A lot of problems in statistics, matrix completion, linear regression can be formulated this way. A lot of problems in physics, like scattering, can be formulated this way. A lot of problems generally in math, like solving PDEs or integral equation of the first and the second kind, can exactly be formulated this way. And in many of these problems, it is kind of relevant to consider the infinite dimensional setting, where this object can be continuous, and then you have to worry about discretization somehow. So the issue, so what we want to do now is think a second more about this problem, think what are the issues, and then start to propose some possible way to solve this. Okay? Once we're going to have it, we're going to just try to go back there, find the connection, and then later on recycle the same approach. Are these questions at this level so far? Are the elements clear? So you see from the way I draw the picture that I'm already encountering a problem, which might be that this problem might not have a solution. If either G or G delta, but especially G, does not belong to the range of the operator, it means that I cannot find the point here that is mapped into G. It just doesn't exist. Okay? Even if it was here, I might have that more than one point go in the same solution. So, sorry, is mapped in the same point. More than one element of the possible solution is mapped into the same point. And then which one do I want to pick? So I might have a non-uniqueness problem. And lastly, if my data are corrupted with noise, I have to wonder what happens where I move G delta inside of here. I don't want the solution to go crazy and explode, because otherwise it won't be anything practical. These three issues are at the nature, the basic idea of what we call the well-posed or ill-posed problem. So the idea goes back 100 years, and the basically three requirements are existence. Say, in our case, we can write this as saying that G has to belong to the range of A. Uniqueness. This would be the case if the kernel of the operator is empty. And the last requirement is continuity. Or, let me put in parentheses, stability. The idea here is basically, let me just write it in a kind of an informal way. If you could do A minus 1 G delta, okay, suppose for a minute that you can actually invert the operator just as it is, okay? Then you could just apply to G delta, and then you have to wonder, okay, what happens if I change this slightly? Well, let's make it simple. Let's assume that this is just, everything is finite dimensional, this is just a matrix, and let's make life even simpler. Let's assume that this matrix is diagonal. so that when you invert it, you just have to take the diagonal elements and take the inverse on the diagonal. It means that basically this is just going to be something with some numbers, 1 over sigma 2, 1 over sigma n. These are just some numbers, and let's assume that these numbers are ordered so that sigma 1 is the biggest and sigma n is the smaller. What you see is that when you now apply this to this g delta, well, you're going to have everything amplified by this 1 over sigma n term. If sigma n is tiny, this is going to blow up everything it encounters. So if you have even a tiny difference in this delta, you can get two completely different solutions. If the problem is finite dimensional, you always get a solution, but basically the condition number of the matrix you start from is going to be very important. And if it has a bad condition number, you are very unstable. If you are in infinite dimension, it can be even worse because the inverse might not even exist. Okay? The smallest eigenvalue can be 0. For example, if you're dealing with compact operators that appear in all branches of applied math. So what do you do with it? Well, the idea is that what you do is that you want to cure this by somewhat increasing the condition number. There are many ways of doing this, but the idea is essentially that we want to try to solve each of these problems, and we're going to begin by rephrasing the problem in a least square sense. So we're going to say that essentially that rather than trying to find an exact solution, we're going to settle for an approximate solution. So basically, what do you do? So if this G doesn't belong to the range, but you still want to find the reasonable solution, what is a reasonable solution, you think? I have to find the point here which is reasonable, even if G does not belong to the range. What do? You take this guy, you project in here, and then you go back. Okay? How do you do it? Well, you're basically saying, among all the F's here, map them here and find the one closest to G. Okay? Clearly, you're not in infinite dimension, you're not ensured this problem to even admit a solution, but this is a weaker assumption. So instead of requiring G to belong to range of A, the set of minimizer of this is actually going to be different from empty as long as the projection belongs to the range. Again, if you're used to finite dimension, this is trivially true. If you're in infinite dimension, when you project on a closure. So this is basically saying you're not on the closures, you're really inside. Okay? So it doesn't matter too much. This is the technical definition you need. You just can appreciate that this is weaker than this because you don't want the point to be inside, but just the projection to be inside. Now, this provides you some solution that now exists, but there can be more than one. Okay? If this operator doesn't have a trivial kernel, here you have many possible solutions. Okay? And then what is typically done is among all these possible solutions, pick the one with minimal norm. So among all the possible solutions in the least square sense, the one with minimal norm. And it's easy to show that it's unique if I take here just the norm in the Hilbert space. So I'm a bit, I don't know if you, hopefully you don't get confused. I'm not writing explicitly which norm I'm using. This is the norm in G, and this is the norm in H. Should be clear from the content. You just stop me. All right, so we wanted to solve this. We had a bunch of problems. How far are we in fixing them? Well, we had existence, done. We had uniqueness, done. We had continuity. Are we done? Well, not quite. You can easily check that this can also be written just as the pseudo-inverse of A object, but still once you're given empirical data, this might have a very bad condition number. You just throw away something, but you're not ensured that that you have any kind of continuity in any sense. In fact, it's a standard result that in infinite dimension, so that basically this guy is going to be bounded only if we are in finite dimension. Okay? So what do we do? Well, we have to, up to now we've been precise. We have not taken into account the fact that you just have noisy data. We just settled to say, okay, if I don't even have a solution, I cannot even start to try to make sense of the problem. I have to define a solution. So this is going to be our target now. It's the new target of an inverse problem. We still have to deal with instability. And basically, this is what regularization theory does for you. So the idea, and I'm just going to present the basic idea of Tikhonov regularization, is to consider the following problem. Which is not one problem, but is actually a sequence of problems. So I consider the squared error, and then I penalize with the squared norm, and I introduce now a parameter that is somewhat a weight between these two terms. I'm now considering this, what happens with this when I have my noisy data, okay? In some sense, if you want, you can view this as a relaxation of the previous problem. You take this problem and you just solve, you're taking the constraint in an exact way. Here you take a Lagrangian formulation where you relax the problem and you now insert a parameter lambda that in some sense control how much you're relaxing the problem. And the idea is that lambda now is going to somewhat do the job of controlling how nice is my solution. If lambda is very small, I'm basically going back to this case. If lambda is very big, I'm basically ignoring the data, try to get something which is very simple. And this indeed can be further derivative of this. If you just take the derivative of this term, you get a star a f minus g with a 2 plus y lambda f equal to 0. And this tells you that you have to consider a linear system. And here you see, from a numerical point of view, so if you want, this is kind of just a variational perspective. I have a problem, I relax it, now I have an extra parameter. When you take the derivative and you look at them, you actually get a numerical perspective on this. You had the matrix, you had to invert it, it might be unstable. Now you take basically a related matrix and you add something on the diagonal, so that if the eigenvalue here is small, you're going to keep it up. Okay? You're going to just raise it a little bit. And then you apply it. Okay, is this a good idea? Can we really show that from this we can get a good solution? We can get something close to F-dagger. The problem is, again, it's similar to the one above. We have an empirical problem, in which sense it gets me something close to the original problem. And you see that immediately we will have to stop cheating. Where did we cheat here? Well, I sneaked in a parameter lambda. It is going to do something, and I didn't say how to choose it. This is not an algorithm, it's a half algorithm. In practice, you open up and you say, no, you choose lambda. Well, if you don't tell you, this is not a real algorithm. And of course, in practice, it's going to matter. If I choose a bad lambda, I cannot hope to get a good solution. It's going to depend on the noise. And here, the theory explodes in a bunch of different ways, and I'm just going to give you a basic result. The basic result essentially says that if you choose lambda, let me see the process. Lambda delta. So essentially, if you choose lambda so that this quantity goes to 0 and lambda goes to 0, okay, so you choose a lambda that depends on delta, so that this ratio goes to 0 and that lambda goes to 0. Basically, if you let lambda be proportional to something like, it has to be a decreasing function of delta. Okay? Lambda depends on delta in a decreasing fashion. Then what you get is that you can prove that if you let me call this f delta lambda, then this goes to 0 as delta goes to 0. Okay? if I take these two conditions as delta goes to 0, then as delta goes to 0, the will go to 0. This is actually a very easy result to prove. Let's see what it says. It says that lambda has to be a function. It says something that we could have discovered just thinking about it. If you solve this problem, okay, you're going to get noisy data. Then lambda should depend on the noise. If the noise is very large or big, you should choose lambda in a different way. In particular, if the noise disappears and you don't have it, you're fine taking lambda arbitrarily small and solving this because you don't have any noise. But if the noise is big, then you should regularize more. This is basically what that is saying. Okay? And this says that it tells you why this is a sensible idea from a modeling or estimation perspective, because it does give you a decent approximation of the original problem. I write here just an asymptotic result. And we're going to do it later today. Under some simple assumption, it's also possible to get rates. Okay? And then you get something more. You can say exactly how far you are. There are a bunch of constants hidden, and it might be that in practice, just getting something like this is not enough. You need some kind of more fancy criterion, and we're not going to discuss much of that. This is just a separate chapter of the whole theory, how to be, to choose a lambda in a data-driven way, and say here things like models of discrepancy principle, complexity regularization, Stein unbiased estimator and other techniques are some of the keywords that you might consider. But we're going to be pretty naive about that. Okay, we're not going to dwell too much into these kind of details.
F plus is the pseudo-inverse of G0.
This guy is the pseudo-inverse of A. That's what you asked?
No, F plus is when delta is 0, so it's A
yeah.
plus of G0.
A plus of G0. Yeah, I didn't call it 0, but yes.
So G, there is no noise here?
Here, G is no noise. So G is the exact datum. Okay. If you want, you can call it G, is the limit case for delta going to 0. Okay? So let me make a few remarks, and then we try to summarize. So I actually consider a simple setting of inverse problem here. I'm basically just sticking to the square loss as the way to measure the discrepancy of in my data. And I'm actually just considering a simple L2 norm, a Hilbert space norm in the ambient space to somewhat enforce regularization. The last talk this morning was basically a big exercise in, well, exercise, a big project in how to be general in both and still be able to get good optimization. Of course, here I'm just not talking about optimization, I'm just talking about how to be sure that this is good from a modeling or, say, an estimation perspective. I think this, in terms of remarks, is basically it. Let's just digest 1 second the board. In this case, that is learning problem in a board is actually inverse problem in 2 boards, so you start to be already somewhat more material. Let's just try to navigate the main idea. You have a linear equation, possibly in infinite dimensions. You do have access to the operator, but you don't have access to the datum. You would like to solve this, but you're only given some approximation of the data. And by the way, a remark that I should have done, I assume deterministic noise. The theory easily extends to stochastic, easily, I don't know, but it extends to stochastic noise that it has been done. The operator itself can be corrected with noise, either in a stochastic or deterministic sense. That's also subject of studies, okay? So I stick to this because that's what matters to us now. So this is what we want to solve. We have these 3 issues: existence, uniqueness, and possible instability. And the drawing gives you an idea of where this stuff is coming from. And then the idea is, okay, let's fix this. Let's consider a set of what is called generalized solution. And let's take the minimal norm solution, what is called the pseudo solution or Moore-Penrose solution. We fix the first 2 issues. We are still stuck with the dependence on the data. Let's fix that too by considering somewhat a variational approach. We consider a family of problems depending on a parameter, and then we effectively reduced our scheme in a 2-step procedure. First, we have a sequence of problems depending on lambda. Then we have to find lambda, and then we get a good solution. a simple optimality condition gives insight on the kind of computation you have to do. In this case, you just have to solve a linear system. It gives you insights on the numerical effect of adding this term, which is basically preconditioning, if you want, making the condition number better. And since condition number was actually giving rise to instability, that seems like a very plausible idea. And lastly, if you want to have a theorem that I write with not much fuzz, which is classical, and is basically saying that, yes, in a precise sense, if you do what you basically can think you should do, that is choosing lambda depending on the noise in a reasonable way, then you can get this to provide a good approximation of your least square minimal norm solution. Okay? Say it again. Yes. If you choose lambda that goes to 0, with yeah. That's what's written here. So this is basically saying pick lambda going to 0, okay, with delta going to 0, but not too fast, okay?
Suppose delta is already 0, so you cannot converge it to 0. Yeah.
So no, if delta, if you take the limit in delta going to 0, you get a convergence result. If you don't let delta go into 0, then you're going to get a bound, okay? And you get basically that this is less or equal than square root of delta, imagine. Something proportional to essentially square root of delta, because we're looking at the square. Or maybe not, just, I don't remember actually now. Well, it depends, because I cannot say this because it depends on some assumption. It's going to be, say, under some assumption, typically you can expect this to see some decaying function of delta, okay? You need some extra assumption. The result I told you is basically without any assumption other than existence. This is not enough to get rates. But if you have delta that doesn't go to 0, then you're going to get convergence. You just get the bound. You can just say how far you are.
So we cannot say anything about the problem without noise. We cannot say something.
No, so what you can say, so the other question is what can we say if you have no noise? So let's look for 1 second about this problem. Yeah. So you can say that if there is no noise, if lambda goes to 0, you know that you converge to this. Okay? If you solve if you introduce this guy, you solve the problem with no noise. Typically, you cannot do it, but mathematically you can. And then you have this solution, and then you can say, for lambda that goes to 0, does this converge to this? Yes. Yes, it does. Okay? But you can also ask how fast. And then that you cannot answer unless you make extra assumptions.
Okay.
Okay? If you put now this together when you have noise, this is the reason why with extra assumption you can do more than that. You can say, if I have noise, but I don't let it go to 0, tell me exactly how far you are. Basically, you're going to put together how fast this goes to this, okay? And then how far away the solution with and without noise are. And we're going to see it later on. I'm basically going to use this in the case of learning theory.
Okay. Thank you very much.
Yep. I cannot believe that you are not killed by these 2 rounds of definition. So I'll drink. Any questions? Okay, so why the hell are we doing this? Because I'm going to infer to you more pain now, okay? So I gave you a bunch of definition, I gave you a bunch of definition. Now I'm going to give you more definition to make the connection, then we're going to be done. Why are we doing this? You see that there already start to be a bunch of mathematical tools that were not present there. I used to have a notion of Moore-Penrose solution. I have a notion of regularization. I have this idea of, well, Postman, which seems like pretty nice. You know, when you have a problem, just stop a second and say, can I solve it? Do I have more than one solution? Are those stable? Well, we are not talking about that at all there. Okay? So you start to get both ideas and some mathematical tools. And if you look in the proof of things like this, or in how you show the answer to the question I was, okay, you have actual mathematical tools and techniques. And so one hope would be to try to steal them, essentially. So the question is, can we turn that problem into this problem? Now, depending how precise you can argue, say, duh, of course. Or you can say, well, I'm not sure. You can say duh, because you can say, well, I have something I don't know, something that I know, I'm Italian, I can just approximate, whatever. But then you can also say, okay, where is the linear operator? What are the two spaces? Where is the noisy data? That's also stochastic. Here there's no stochastic, but there is all this linear structure. And long story short, that in general, it's actually not so easy to massage that problem into this. We're going to have to make some more assumptions that are somewhat strong, but also fairly common. And then we're going to see that we start to see a lot of linear structure. We're going to see operators popping out. We're going to see some kind of strange stochastic discretization noise plus some more normal noise popping out. And at some point, we're going to have something essentially similar to this. Okay? It's going to be a bit abstract, as I told you. We're going to have a bit of time to digest what it is. But once we have it, well, it's just a linear inverse problem. So we can just go in and just check exactly how much stuff we can steal from this world. So that's what we want to do next. Make the idea that that problem is really something like this, precise. The only thing we have to do, put this up. Nice. All right. At that level of generality, there is no inverse problem in sight. Okay? Maybe there is in some very vague sense of some procedure to do whatever something, but there is definitely not something linear. We're going to have to make some assumption. And the assumption really are going to somewhat change the problem. We're going to make a big assumption. It's going to be abstract, but the nice thing is going to be short to state. We're going to basically introduce the space H, which is going to basically be a space of candidate solution to the learning problem. Rather than looking at the problem in that full generality, we're going to try to take a space H of candidate solution, which is not the whole space of all possible functions, but can be really large in the sense that, for example, the minimizer of that functional over H could be the same as the minimizer of all possible functions. Okay? So this H is not going to be a small space. It's going to be a large space. It's not finite dimensional. It's not a ball. It's not compact. It's going to be a Hilbert space. So it's going to be a subset of the space of all possible functions. And we're going to make just two assumptions. The first one is, well, they're both not that innocuous, but I'm going to try to argue that they're not that bad. The first one is that it's a Hilbert space. Okay? Why? If you're thinking about probabilistic and statistical question, this is actually typically much more structured than what you need. If you're trying to prove, say, law of large numbers like result, assuming that much structure is not needed. But try to do any kind of computation without this assumption. Yeah, there are Banach spaces, but try to do a Banach space with no, taking a Banach norm in a Hilbert space is one thing. Try to work with no inner product structure whatsoever. You can do it, but it becomes all very complicated. So this is a strong assumption, but we're going to try to make our life not immediately hard. Okay? You can generalize a lot of things of what I say to Banach spaces. It just gets horribly more heavier from a mathematical point of view, because essentially in Hilbert spaces duality is easy, whereas in Banach spaces is a mess. So there is much more notation. But roughly speaking, everything goes through. This is not the main assumption. The main assumption is the next one, which is that essentially, in words, we want to make sense of what does it mean to evaluate a function. Okay? We're going to want to make prediction and evaluate function. We don't want to sample our function and have values of function at points. We basically want to give some properties of this operation. Okay? And the property we want to say is that the property of evaluating a function at the point should be continuous with respect to the norm in H. So what is an evaluation functional? Given x in x is a function from H to R that takes f and returns the value of the function at the point. It's not a particular original name, I would say evaluation function probably. Okay, just you take a function and you evaluate. What does it mean that it's continuous? I think it's continuous in the normal, in the standard sense. Particularly it means that if you have convergence in H, if you have two functions, and this goes to 0, then for any x, so then you have that for x, you have that f of x minus f prime of x also goes to 0. Okay? That's it. That's our assumption on the space. This is going to be enough to turn that problem into this problem. That's it. That's all we need. Okay? Let's appreciate 1 second what the hell we did. Both these assumptions, we cannot find them in spaces that we usually use, but typically not together. If you take, say, the space of square integrable functions, L2, just in one dimension, then of course it's a Hilbert space. You have just the square norm and then use the related inner product. But is it true that if you have an L2 convergence of two functions, then they're going to be equal at points? No, because L2 is this annoying thing that you're just basically looking at the area under the curve, and if whatever you do at the point doesn't really matter, you can just change it, right? So no, you don't have it. Okay? So you have this guy, but you don't have this. What about this property? There is a norm strong enough to control what happens at every point. Tell me two spaces of function that you know if you don't want to be fancy. L2 and the space of continuous function. L2 we already killed. Let's kill continuous function. Of continuous function, what is the natural norm? Is the sup norm. At every point, you just measure the distance of the two functions at every point. And of course, that norm is basically this one at every point. If that goes to 0, this goes to 0 too. What is the problem? Well, that if you might remember that the continuous function don't have a linear inner product structure. It's a Banach norm. Okay, you don't get the first property. So in some sense, we're going to take continuous function and L2 and smash them together into one assumption. Now you can ask, is this an insane set of assumptions that no space satisfy? And a strong way to say it is that it's hard to find the function space that is used in practice that doesn't have these two properties. You can invent many, but try to tell me one space that you use that doesn't have these two. It's not so easy. Okay? And standard example, we're going to see more, but say, for example, band-limited functions. There are spaces like this. They're not the whole L2. They're a subspace of L2. This is a space. Sobolev spaces, they have this function. If you take combination of Gaussians, they have this function. You take any finite, depending who you ask, some ability condition, it's again one of these spaces. So most of the spaces that we build and use in practice, they tend to be spaces that satisfy these two assumptions. Okay? And I'm going to tell you a few more words in a minute. So far, so good. Now, at this point, unless you know math pretty well, it's not so obvious why this assumption is going to buy me a linear operator structure into the top problem. Okay? We're missing one piece of information. And this is, I just checked on the internet the right spelling, so for once, I'm going to, if this is recorded, it's not going to be wrong forever. Ritz lemma. You know Ritz lemma? It basically says that if you have a functional, so something that maps vector into numbers, and this is continuous, that's exactly the assumption we're making, then you can just represent it as an inner product of some magic element in the space. So here I just say, this is all I can say. But if under this assumption, this lemma basically says, you can say a bit more, you can say that this, which is equal to this, is actually equal to the inner product of f times some representer. That's the name you give to this guy. Okay? It's a deep result. It's not an obvious result. I personally don't have any intuition try to explain you why this buys you that. But it's a very standard result. It basically tells that, it tells you there is a duality between continuous functionals on a Hilbert space and the Hilbert space itself. Whenever you have a continuous functional, you can just identify this with element in the space. Okay? So now, this is a definition, this is a standard result, and now you see that there's some magic going on, because what is this doing for you? It's somewhat modeling in a linear way the operation of evaluating the function, or if you want, sampling a function at a point. And that's basically what we wanted to do, because we wanted to try to extract a linear structure from that problem over there. So provided with this kind of abstract story, that's exactly what we can do. Okay? So I'm keeping up to my promise, okay? For a while, we're just going to introduce mathematical objects, and the question, what the heck are they, is fair, but you have to wait for it. Because for now, I'm just trying to define mathematical objects. We're going to turn that problem into that, and we're almost done. Then we're going to try to do some more gymnastics to understand what is the nature of the object. For example, what are the spaces H's? Can you give me an example? What am I really doing? What is K? What is the role? So on and so forth, okay? One last step first. So let's do a warm-up. Okay? The idea of looking at function approximation as a linear inverse problem is not new at all. Okay? It is known, at least from the 70s, that you can, to some extent, turn a function approximation or interpolation problem in a linear system, exactly doing this kind of assumption. But this was typically known if you just consider a finite set of data points. So that's what we're going to do first. Okay? So suppose that you just have this problem. So you have discrete, you're in the discrete setting, which is, if you want, what you do in practice, okay? You're in this setting, and this is the problem you want to solve. Can I write this problem as a linear system? Well, for any generic f, no. But if I assume that my f comes from a space with these two properties that I know, then I can represent function evaluation like this. Can I do it? Well, yes. Why? Well, because I'm just going to write, let me introduce an operator, S, n, that goes from H to Rn. And what it does is that it takes my function and it maps it through this operation into the value of the function at the point. Okay? I can write f of xi just as the action of a linear operator, which is in this case just a collection of finitely many functional. The evaluation in x1, the evaluation in x2, up to xn. That's it. All right, but then I'm almost done, because now just take this y1, yn, and just stack them up into a vector of size n. Let me call it yn. Then I can just consider this linear system. It's a linear system, okay? Pretty general. I have to make some assumption, this one. And I told you, this is known since forever. And now we can stop 1 second and ask, are we done? Is this all we need to do to turn that problem into this? Not really. Why? Well, the solution of this problem is, I mean, this is definitely what you can do in practice. This is basically going to be the kind of problem you can solve in practice, the one given on data. But that's not what we want to do. That's what we can do. What we want to do is solving that problem, or try to find an approximate solution to that problem. What is the regression function has to do with this? I would like the regression function to be somewhat related to something like the pseudo inverse solution, okay? And here I'm close, I feel it, but I don't see it yet. I have an empirical problem that I can write in a decent way, but I'm still missing out on the true problem. So that's what we want to do next. And this step, a little bit like this, is going to be somewhat abstract. Roughly speaking, what do we want to do? What is the ideal setting? This is the discrete setting. What is the ideal setting? Let me try to emphasize one part of the question. This is a discrete setting. What is the ideal situation? continuous setting. Continuous with respect to the what? To the data. What does it mean? Well, instead of having a finite sequence, you have to basically consider all possible data points. Okay? So roughly speaking, the idea is that we can turn that problem into this if you consider some kind of continuous version of this problem. So let's introduce the space L2. So in some sense, we need to introduce the continuous version of Rn, okay, when we let the number of points go into infinity. And the idea is that this is going to be the space of function from X to R, which are bound with bounded norm, L2 norm. Importantly, this is just L2, but it's L2 with respect to the marginal distribution, okay? Not to the Lebesgue measure of anything. Lebesgue measure might not even exist here. The idea is that this is going to be basically the continuous limit of this Rn. And this can actually be made very precise. Then we're going to introduce an operator that takes function in H and view them as function in L2, basically just evaluating them. So this is just the, just take it a bit formally. This is the continuous version of this. Here I'm evaluating the function only at the training set points. Here I am evaluating the function at every possible point taken from this measure. And so in some sense, I take a function and I view it as a function in L2. Again, this is a bit abstract. Okay? This guy, the nature of this guy is not obvious. For now, basically what he does is that he changes norm. I have a function in H, and I just don't want to view it as a function in L2. Its discrete version is a bit nicer. You can view it as a sampling operator. This is, we'll see that it's going to be something like a restriction operator. Okay? Something that restricts a function defined everywhere to function defined only on the support of this. You have this restriction operation. Well, now I have to take just the continuous limit of this, and the idea is to consider this problem. Okay? So in words, this says, oops, yes. Find the function in H which is close to the regression function in an L2 sense. If the regression function is a function in H, I can find it. If it's not in H, I'm in that situation where I have to project. And then I can define and keep on going. So let me close, let me get some space. So write down this problem. Solve S F F rho given Sn and Yn. Okay? So the ideal problem is to, so what did I do to go from there to here? I restrict myself to look for solutions within a large Hilbert space H. Then I'm basically saying, among function in H, I want one which is close to a rho in an L2 sense. But I cannot do it because I don't have access neither to the operator that I can evaluate the function everywhere, or to the true function itself. What I can do is that I have access to an operator I can evaluate at points that are finitely many and given, and I have n values of the function if you want. So that's all you have. This is indeed the linear system, and this is somewhat a kind of a strange noise model. Okay? So one question which we're going to answer in a minute is, in which sense this is an approximation of this and this is an approximation of this? The difficulty is that this space starts from the same space, but they end up in different spaces, so I cannot just take the difference of them. Okay? I will have to do something more. I can view this as some kind of stochastic discretization of the one above. And similarly, this is a function, but this is just a vector. If you want, the other thing is that this doesn't quite look like that yet, but you can write a couple of expressions that make this more apparent. 330. So this is just a linear system, okay? But let's look at the Moore-Penrose solution first. Well, now we just have to, we're in the land of inverse problem now, so now we can start copy. So I'm going to just write what is written there and copying it down. So I have to write argmin of S rho F rho square, where this is the norm okay. This is going to give me H0. And then, if you want, let me call the F dag rho the argmin of F with the F in H0. Now, a very easy observation is to show that this is essentially the same as what I call EF over there. So, an observation is that let's see. It's a standard fact in, in statistics. We use it all the time. If you take the risk, the expected risk I define over there, is essentially equal to exactly this norm plus a term, which is the risk of the best possible function. This is a very standard fact, and the way you prove it is just that basically you take, you take these two guys, you take these two guys, you take the square, and you just see what happens, and you just remember that the regression function written over there is exactly the mean with respect to the y. So when you take this integral, remember the integral depends both on x and y, just decompose the measure and just let it go through, and then you have this equality. It's very simple to get, okay? But now if you accept it, rather than asking how you prove it, what you have is that the Moore-Penrose solution of this is exactly solving that problem on your space H, okay? So this FH rho is exactly the Moore-Penrose solution of the learning problem, where basically it's natural that we have to settle for something like the regression function because we restrict ourselves to space H, which is potentially smaller. Okay? If it's large, say if it's in some sense dense in a suitable sense, this might be a minor assumption, but in the typical case, in the general case, we might have to project. And this is the new target of learning. If you want, is what it might call the best in the model. We're not assuming the problem to be well specified, but we're assuming that we can get the best in our class. And again, for now, this is a large class. It's not a ball or a compact set. It's a full Hilbert space. Okay, so this, if you want, closes a bit the formal connection. Let me write one more thing, and then we make a few comments. I left you a bit with the idea of how do I compare these two problems. Well, notice that if you have a problem like this, you can just take the derivative like the optimality condition, and you get what is called the normal equations. The normal equation look like this. Okay? You just take the derivative of this, as we did before, and set it equal to 0. Then you just get this guy. If you can do the same thing for this kind of empirical problem, you just have to replace this gives you an insight to how you might be able to measure the distance between the empirical problem and the true problem. You cannot compare them directly because they live in different spaces. The operator live in different spaces. But if you go down to the normal equations, You can, because now this is operator from H into L2 back to H, and this is an element that sends something in L2 into H. Similar here, you have something that takes H, send it to Rn, and then back to H. So this is from H to H again, and this takes a vector in Rn and send it into H. Okay? This idea is actually we discovered after we discovered it, that it's not new. When you typically study discretization of operators, that is, whenever you have a continuous problem, you have to go to a discrete problem, use exactly this kind of quantities. And this is used in inverse problem, but in particular in a setting like econometrics, and it turns out also to be useful in learning. Okay? And this, if you want, start to somewhat close the picture. We started from that problem, we introduced this other problem, we make one assumption, and now we end up with the linear system. The big assumption here is let's restrict ourselves to a big function class, which is a Hilbert space with continuous evaluation functional, and then we can write down a linear system, so a linear inverse problem with some kind of where we only have partial knowledge of the problem, both in the operator and the datum. And then we have two observations. One, the least square problem associated to this inverse problem is exactly the learning problem we had, up to the assumption we made, which is restricting to H. And two, if you want, this is linking to the learning setting. The difference with the inverse problem is that it's a kind of uncanonical noise model. It's not the usual noise model. The usual noise model is just say, oh, this is different, you know, this is just a norm away from that. We cannot do it now. We're going to have to take somewhat the difference between these two and the difference between these two. And this is going to be our noise model. And then, if you want, this could be abstracted and become a very general theory of how you essentially discretize operators that somewhat admit some kind of linear representation. Okay? Okay, let's breathe 1 second now. Okay, so let's look 1 minute. So there is some nice part and somewhat annoying part. The nice part is we promised that we were going to get a linear inverse problem, and we did. Okay, and indeed now we can go in and start to use it by taking stuff from the theory of inverse problem. We're still a bit left with, okay, what are this stuff again? This guy doesn't look that bad. Okay. Basically it says take a function, evaluate in a bunch of points. The typical name is sampling operator, not particularly originally. This guy is a bit weird. It takes a function and changes the norm. What is it really doing? One setting where it becomes a bit, these operators are not that weird. They're embedding operators that take two spaces and just take a function and view it as a function in another space by changing the norm, appear all the time. Okay? And the problem of solving an embedding problem, a linear system induced by an embedding operator is not uncommon. And so this is just a special case. Yet, the sole operation of changing a norm is something that one doesn't appreciate too much. There is at least one case, or at least two cases, let's say, where these objects become a bit more tangible. Or maybe, let's see. One, I already hinted it in words a minute ago. Let me write a couple of things. I introduced the space X, and I put on it the marginal distribution rho X. As I told you, the prototype example is X, very high dimensional space. But as much as that's the prototype example, similarly, we typically think of rho X not to be the whole space. Okay? Say, if you take images of faces that are 20 by 20, these are not all possible pixels in 400-dimensional space. In fact, if you take any random point in 400-dimensional space, it doesn't look like a face. It's going to be what? Well, it depends who you ask. If you want to do math, you might say it's a manifold. If you just want to say what it really is, it's going to be, I don't know, a pancake of some kind, but it's not going to be the full space. It's going to be a smaller chunk. Okay? So the simplest situation, in low dimension, think of just an interval. Okay? So let's define X rho to be the support of rho x, and this is contained in x. Say the simplest case is I'm in low dimension, x is the real line, rho x is just the measure on an interval. Okay? More general, you can say x is R3, and now I have some domain of some kind in R3. Okay? And then you can decide what kind of properties you want to put on it. For now, we just assume it to be the support. What is this operator doing? Well, the function in x, in h, don't know. If you see nowhere in the definition of h, there is any dependence on the measure. H is just a space of function defined everywhere. So when I'm considering the operation of evaluating the function in this sense, I'm basically restricting the function to be supported only here. Okay? If you think of this to be function defined everywhere on RD, and this to be a manifold, you're basically trying to find the function defined only on the manifold. And since the manifold might be something you don't know, this is an interesting operation. You're basically saying, I want to learn something on the manifold. How do I do it? Well, I first learn a function everywhere, then I project it down, and then I go back. I'm going to do a restriction, and then I'm going to try to do some kind of extension. If you look at the adjoint of this operator, the one that goes back, okay, it's an exercise to show that it's just going to be some kind of harmonic extension. So you take S star G, so if take a function in G and consider the transpose of that operator, the adjoint of the operator S. The operator S goes from H to L2. The adjoint is going to go from L2 to H. Okay? Using this explicit form, which I deleted or didn't write. Oops. I deleted it. I'm going to write it here. So the operator S rho of f of x is just, it's not readable, sorry. S is just the inner product of f and kx. If you use this expression and just check what is the adjoint, remember the adjoint is just the thing that says sf equal g has to be equal to f S star G. If you just use this, the definition, then you get that the S star rho is this operator here. What is this doing? It's basically saying, if you give me the value of this function on rho, I'm going to try to define it everywhere for any possible x. And I'm going to do it by basically taking the value of this as averaging with respect to this quantity, which is just the inner product of kx and kx prime. You can view this as a function of two variables that somewhat measure how related are the 2 points. Okay? So this is what is called the harmonic extension of the function. So this operator, again, becomes somewhat more tangible. Okay? The operator itself, in the discrete case, is just a sampling operator. In the continuous setting, is a restriction operator. The adjoint is an harmonic extension. What is the equivalent of this in the discrete setting? Well, you will have to just replace the integral with the finite sum. And what is it? Is what is called the out-of-sample extension. I give you the value of the function just at the training set points, and you want to extend it everywhere. Okay? You just do the same expression with the sum instead of an integral. Okay? Okay, so this makes the object a bit more transparent. Let's try to consider a particularly simple case. Suppose now that we consider H to be just the space of linear functions. Okay? It's okay. It's a linear space. Okay? And you can easily check that the evaluation functional continuous. What you can show easily is that if you look at, basically what you have is that if H is the space of linear functions, basically each function is identified by a slope. And so what you have is that you can identify this by Rp for some P. Okay? So again, each F, which is going to be now W transpose X for some W, and so F is roughly equivalent in H, is roughly equivalent to a vector in Rp. Okay? That's a special case. What is my operator Sn? Well, it's an operator that goes from Rp to Rn. So it's just a matrix. Which matrix? Well, it's just a n by p data matrix. Each row is one of the example. Each column is one of the coordinate in this space. Okay? And so we're recovering basically the standard linear regression setting. Okay? Just as a special case. Again, this object is a bit friendlier. The nature of this object is a bit stranger. Okay? It will be basically the operator that, given a vector W, evaluate it in every possible point X that I can sample. So S rho is kind of, if you want, one way to visualize it is an infinite matrix with infinitely many rows, but finitely many columns, even by the fact that I'm working with finite dimensional functions. And this game is going to give me a way to, this kind of idea is going to give me a way to compare these two objects. Okay? It's interesting to notice that this operator, S star n, in this case just become X transpose, let me call it Xn, X transpose X, which is the second moment matrix. So the kind of technique that we're going to have to use to compare these two objects are essentially covariance estimation techniques. We're going to have this is going to look like an empirical covariance, and this is going to look like an expected covariance. And this is just, again, going to look like some kind of empirical mean and expected mean. So in this kind of approach, there's going to be a lot of gymnastics from essentially a functionalistic point of view, but where if you ignore the infinite dimensional nature of objects, and then you're just doing linear algebra. So you're going to spend 85% of your time doing linear algebra and stealing from inverse problem. Then at some point, you basically have to use some law of large numbers to control quantity like this and their expectation. All right, so this is basically all I wanted to say for this first segment. So let me try just to summarize a bit and breathe. Again, this is going to be the most abstract and somewhat useless part of what we're doing. It's going to be somewhat the foundational part. Okay, we're going to build on it. My hope was to devise some technique that will allow me to rewrite the learning problem, which is the problem of finding a function that will make small error in the future with respect to a fixed unknown distribution, given a finite amount of data. The goal was to relate it to an inverse problem, which is instead the problem to solve a linear equation where I don't have access to the exact data, but only to a proxy to it. The reason why I want to do this is because this is a very well-established theory. There are many, many techniques, both in terms of what do we mean by a good solution and a bad solution, and also how to find such good or bad solutions, introduced in standard concepts like pseudo-inverse and Moore-Penrose solution and Tikhonov regularization. The connection costed us some sweat because essentially the problem as it is does not have a linear structure, but the moment I make enough assumption to explain in a linear way what does it mean to evaluate a function, then linearities start to appear. I can define a sampling operator that takes a function and maps into the finite data, or somewhat a continuous version that I can view as a restriction operator that takes a function defined everywhere and just evaluate on the support of the marginal distribution. The ideal problem now becomes find a function in H which is close to the regression function in L2, a problem which might itself be ill-posed, and I might have to pass to a pseudo-solution. The practical side of the story is that all this stuff won't be possible directly because we don't have access to this object but only to their discrete version. Okay, so the job of the theory would be, once you devise a way to use this to build a solution, prove that you can get something like this, that you can get something that tells me how far you are from the original problem. And this is going to give an analytical part and then a probabilistic part that allow us to control the nature of this noise. Okay, that somewhat mixes up the noise and the sampling, the discretization and the conditional distributions. The whole game now is going to be essentially go towards algorithm and just build algorithm and then analyze them. And so the next segment is going to be essentially just basically doing that and proving this kind of stuff. Tomorrow we're going to move on to more interesting algorithms. I think I should stop here.
Questions?
So you said it at some point, but there's no restriction on X beside being some kind of a metric space on the capital X.
No?
For this theory to hold, capital X could be...
I know that it works. So essentially, it relies on this reproducing property. The reproducing property has been well established for Banach spaces, and then for some fancy topological spaces that I never take a look at. I don't think metric space might be...
No, but I'm sorry, I'm just speaking about the capital X space, not about H. The ground space. X, capital X.
Oh, X, yeah, basically what you need on X is that you have to be able to disintegrate the distribution in marginal and conditional. That's all you need.
It can be a functional space or whatever.
If you want, it's all hidden in, yes, it can be whatever you want. You know, the RD is the classical example. The game is going to be how to build function spaces on it. So the real question is, okay, but if you give me, say, a space, which is a space, so for example, any discrete space would be fine. So strings, graphs, a structure of any kind. The question is then how you build function spaces on it, okay? So how you build the space H, which is a Hilbert space with continuous valuation function on the space of graphs, then become a question in its own right. So a big, if you want, a big beast is hidden in this choice, which is free in the theory so far, but it will depend on the kind of X you consider.
And is there a canonical way to always define this, or it's like the open problem of designing kernel is there's no answer?
This is the blind deconvolution or data representation problem.
So the IID assumption that you have considered at the beginning is a key part for proofing techniques, or you can extend it for any correlated, samples?
So
or
roughly speaking, the one I, the identical part, is crucial because we are defining the problem based on that. There are some attempts to go beyond it, but it's more substantial. We can discuss it offline, but it's more substantial. The other I, well, you can weaken it a bit. If you basically, in everything I said, is only going to enter once we have to control this kind of quantities, so this kind of empirical covariances with respect to their expectations. So whenever you can make a dependence assumption that allows to estimate covariance, you're going to be good to go. That's basically the story. So some kind of mixing condition for which you have law of large numbers are going to be good enough. That's basically what you need to control empirical covariances. Shout.
Do you in practice mostly rely on the non-identification assumption, that is that the true G does not belong to the range of A, or in general, do you restrict in applications? Do you restrict G to belong to the range of A?
No, in general you cannot, because G is, so in both cases G is unknown. Okay? So you have F row, and you can try to, one thing you can try to do is that, I'm going to discuss it when we start again. Example of spaces H that are, say, dense is the space of continuous function in L2. So in that sense, strictly speaking, it's not there, but it doesn't really matter because in the L2 sense is there. So you can do that. You can take large spaces of functions. But typically the way you build the function space is not just thinking about them to be large, but as we were saying, depending on the problem at hand, if you have, say, graphs or something, or images, then you try to build spaces of functions that somewhat reflect your knowledge of the problem. And typically, you have to give up the idea that you're so good that you're going to put this, be able to always ensure that the right function is in there. It doesn't really play a big role in this story. Just to point you in the right direction. So this is going to point in the direction. The question we want to ask next are, okay, let's do Tikhonov and let's see how we can prove that this is a good way to solve this. And then we're going to ask, okay, what are the computation entailed? Can I do better than that? Can I do better than Tikhonov, meaning in terms of computations? All our effort is going to be in basically keeping the problems and the beauties of whatever I said and just try to keep statistical optimality and shave computation. This is going to be the primary goal, from tomorrow on.
So let's thank Lorenzo again. Thank you.